Okay, kids, so even though I'm sending you the answer keys to these problems, I want to spend a little bit of time kind of talking through some stuff. I'd record this in my room, but everything's been taken out of my room, and so I'm just going to wing it on here. All right, so on this one, here's what's important on this one, is that you're pulling this bar in this direction. And what's happening is that you are exposing more X's in this region. So Mother Nature's going to flip out and go, oh, we need to make more O's. So what's going to happen here is that you have to be able to work this problem. So what's going to happen is that to make O's, to balance that out, take your right hand, curl it so that your fingers are pointing up, so your thumb is pointing towards the top of the page. Okay, so that's the first right-hand rule. So the first right-hand rule, your thumb is going to point up so that you creating dots with your index fingers. Now, so what that means is that your current is going to be going up this rod. Now, the second thing that you've got to be able to do is figuring out which direction the force is acting created by this current moving in a magnetic field. So now you're going to do the right-hand rule a second time. So now you're going to point that same thumb going up. Then you're going to take your index finger. So here's the second one. You're going to point your thumb going up. You're going to point your index finger into the page, okay, because that's the direction of the external magnetic field. So imagine that your index finger is pointing down into the page, okay, and then your other fingers then are going to be pointing to the left. So and this is going to be important once you get to the sum of these forces. So the force from the magnetic field is pointing to the left. You're pulling it to the right, okay? So that force is going to be acting in the opposite direction that rod is being pulled. So when you go down here, you've got a 3 ohm resistor, okay? And you want to calculate the magnitude of the current induced in the loop by the rod, the rails, and the resistor. So down here, okay, so you've got your current, right, which is going to be V over R, but your voltage is going to be BLV, which is your magnetic field, which is that 0.8. Now, this L, listen to me, this L is going to be this 0.52 meters. If you were given this dimension here, that would have nothing to do with the calculation of BLV, because it's only the length that's in that magnetic field. This distance has nothing to do with that. It's only the rod that's moving in that magnetic field. So, you know, your resistance is 3 ohms. You've got your velocity, 0.52. There's your magnetic field. Okay, 0.25 amps. Now, you're also told in this problem that there is significant friction, and you're given the coefficient of friction of 0.20. So this is nice because it ties together some different things. So here's what's going to be important here. The reason that I went through that first process is that you had to realize that because the rod is being pulled to the right, the frictional force and the force from the magnetic field are acting to the left. This is why these two values have the same sign, because if you don't know that the magnetic field force is pointing to the left, you don't know that those have the same sign. So that's why it's so important that you be able to understand which direction that force is acting. Now, on C, they want the energy dissipated. Well, that's just PIV, but I don't know the current. Excuse me, I know the current, okay, because I found that 0.25 amps. And then my voltage is going to be BLV, okay? And remember, that has that weird BLV, okay? That fancy electromotive force is the same thing as voltage. Don't forget about that. And then I want to multiply that by 2 seconds because that's how long it's being pulled. And then the work done is just force times distance, okay? Well, here's my 0.35 newtons, and I have to take 1.8 times 2 seconds. That gets me my distance that it's going to travel, and then I multiply all of those together, I get 1.9 joules. And then on E, it says compare these answers, provide a physical explanation. So keep in mind that this number of joules here, okay, is a lot more because of the fact that this is the force that's also involving that frictional force. So that's why this answer is so much bigger than the 0.38 joules is. Okay. All right. Now, this one, I promise you, what's going to happen here is that you've got this loop going in here. It was the basis of the slab, and you have to be able to work this problem. Trust me. So keep in mind that the front edge of the loop is at x is 0.12. It's 3 meters. Calculate the following: the magnitude of the induced current. Now, here's what's happening. So you're creating x's. So inside this loop, as that passes through, you're going to get an influx of x's. At this point, you're asking yourself, oh, what's Mother Nature going to do? Mother Nature is going to go, oh, I need O's to balance that out. So Mother Nature in here, because you're creating x's, is going to make O's. So when you make O's, then, again, with your right-hand rule, okay, to curl your fingers out of the page, that means your thumb has to point up the page. So that's the direction of my current. Okay? So then, when you get down here, okay, the magnitude of the induced current. So down here, then to get that current, you're going to use I equals V over R. Here's your BLV, okay? Then you got the resistance of 4 ohms. Now, and again, here's what's important. On the next one, when you want to find the value of that force, notice that I'm using 0.10 meters because of the fact that you're told that this height here is 0.1. So that's the dimension that you're going to use when you calculate Bill. This 0.2 meters, nothing to do with it. It's only this leading edge that you worry about. So it's the vertical distance, not the horizontal distance, or whatever the dimension is that's actually going into the page or into that magnetic field. Okay. So then on where you've got that current coming around like this, okay, because that's what I'm showing you here, right? Then what's happening on C, at a time later, the current and loop are completely inside the magnetic field to determine the net force. Now, here's the deal. Once it's completely inside of that loop, okay, or that loop is completely inside that magnetic field, there's no changes. So remember, you only induce a current to oppose a change in your flux or your magnetic field. So since there's no changes, guess what? There's no current. Now, after it leaves, okay, and you begin to reduce the number of X's, then you will induce a current to produce more X's to balance that out. So now with that said, I'm going to jump down to this problem, okay? And with this one, you're dropping a magnet, and here's what's important. You're dropping the south end of the magnet into this conductive ring, okay? Now, so remember, on a magnet, it's the Confederate designation. The field lines are going from the north and coming around here from the south. So what's happening here is that you're going to try and figure out which direction that current is going to travel. So if you look at what's happening from this plane right here, you have magnetic field lines that are coming in like this. So that means this ring is sensing an increase in O's. So to balance that out, we need to make X's. So we need to make X's inside of here. So if you curl your fingers, so here's this ring. So if you curl your fingers in like this, okay, then your thumb is going to be pointing like this. That's why that direction is clockwise. Now, afterwards, okay, and then it falls past, then afterwards what's going to happen is that then you're going to sense a decrease in these lines that are trying to come up from the North Pole. So then, let me redraw that. So once the North Pole has passed, okay, because remember, these field lines are going to be coming up like this. So then that hoop is going to sense a decrease in the intensity of the X's. as it senses a decrease in the intensity of the X's, then, hold on, I screwed that up. You're going to sense a decrease in the intensity of O's. I had that all wrong. You're going to sense a decrease in the intensity of the O's, and then you're going to make more O's to balance that out. That's why that current then becomes counterclockwise. Sorry, I got my X's and O's screwed around. That's why I don't teach football or coach football for any number of reasons. Okay, now, here's another glider problem. Your magnetic field is going into the page, and you want to be able to determine that force. So your X's, you're creating O's, use your right-hand rule. There you go. Now, one of the things on the AP test, and is also true on this test, if I say, what's the direction of the current? You can't just say, oh, it's going in this direction by the right-hand rule. That is way too vague, okay? That is way too vague. You need to say something more specific like, hey, this thing is sensing a decrease in the X's and it's making more O's to balance that out. And then by the right-hand rule, the current will be going in that direction, okay? So you just can't say, oh, by the right-hand rule. You need to be more specific than that. Okay, now let's talk about this big problem. And I promise you there's going to be something like this on the test. I promise you, I promise you, I promise you. So here's what's happening. You have a radioactive source. It's a positively charged particle. So, and on the test, this always becomes an issue. If you're told that something is like a charged particle or it's been ionized or something like that, that just means it has a positive charge to it or negative charge depending upon the situation, okay? And if it's a singly ionized particle, guess what? It's plus Q. And that's typically what happens, okay? So when you see the words ionized particle or a charged particle, that means that it's not a neutral atom. And the reason that we don't shoot neutral atoms into electric and magnetic fields is that neutral atoms aren't affected by these magnetic and electric fields. They are only impacted by, wait for it, charged particles, because neutral particles just go straight through. Okay, so here's what's happening. So if you look at this, you have two situations going on here. You have a magnetic field that is coming out of the page, okay, so you got dots. So if you look just at the magnetic field and you do the right-hand rule, so you point your thumb in this direction, the magnetic field is coming out of the page, okay, so your index finger would be pointing out of the page, and then your fingers would be pointing downward. So just from the magnetic field, that's going to be pointing downward. Now, because of the fact that, so the force in the magnetic field is trying to drag this thing down. Now, to balance that out, because it's going in a straight line, then you have to have an electric field, and this is why the bottom of the field is positively charged. So based upon the electric field is going to try and drag this thing up. The magnetic force is going to try and drag this thing down. So because by virtue of the fact that it's moving in a straight line, I know these two forces are going to be the same. So when you get down here to how I have this thing worked out, which is way down here, you'll get all this. But here's the basis of this, is that I said the magnetic field equal to the electric field, QVB equals EQ, then the charges cancel out, and that's going to be important, so it really doesn't make any difference what it is in terms of this calculation, so you're going to have V1. Then the next part is when you get to the next question, it says determine an expression for the initial magnetic force, okay, and state its direction. So don't forget that little bit right there. So on that part, then on part 2, then that force is going to be QVB. So, but when you look at this, and this is going, you'll see where this is going to play out a couple of times. Instead of velocity, I'm going to put in E over B1. So because that's the initial way that I expressed that velocity. So all I did here was that I took the electric field over magnetic field 1 and substituted that in, multiplied it by B2. Hey, we're off to the races. We've got this thing, okay? And then make sure that you indicate that direction. Now, when you get to C, the magnetic force as it moves into region number 2. So this is the back side of the page. So on the back side of the page, physically what's happened is this. So we had this charged particle coming through straight. It's going to enter this part. Now, then with this one, then you're told what's the magnitude of the direction as the particle moves into region number 2. So now we've left this one. Now notice with this one, we've lost the electric field, and the magnetic field is now going into the page. So we went from dots to X's. Okay, that's going to be a huge thing. So now when you do the right-hand rule again, now your thumb is still pointing to the right, but now your index finger is going into the page, and your fingers are going to be pointing up, and so that's why that force is going to be going in that direction. Okay? All right. So that's the story with all of that. Oh, I forgot about this. I skipped over part 2. So this is very important because of the fact that if you have a speed greater than that first ratio, and that's what I've worked out down here, okay, it's going to occur. This is while it's still in that first region. So you're not going to change the force from the electric field because that's a fixed quantity. But what's going to happen is that you're going to make your velocity bigger, and so the force from the magnetic field is going to be stronger. Therefore, that's going to be bigger, so that's why that thing is going to get pushed downward. Sorry about that. I completely blew over that. Moving on to the next part. Okay. Now, basically, here's going to be the next big thing, is that we're going to, because of the fact that this thing is moving in a circular path like this, continuously going around like this, the magnetic field is always acting inward, otherwise known as the centripetal force. So the whole key to this is that we're going to let the centripetal force equal the magnetic force. And I can almost guarantee you at some point you're going to need to take advantage of something like this. So the force in the magnetic, QV1B2, make sure that this is the second magnetic field. This is mv1 squared. So basically, we're going to drop out one of the velocities. So what they're looking for is this ratio of charge to mass. And this, when you actually started to figure out the mass of an electron or the mass of a proton, the mass of a neutron, we couldn't actually weigh these particles. So we had to figure out a clever way to make this happen. So if we figured out the charge to mass ratio, then once we figured out the value of the charge, 1.6 times 10 to the negative 19th, then we could figure out the mass. So we can't weigh or find the mass of an individual electron or proton. But if we could figure out that charge to mass ratio, then if we know the charge, then we can solve for the mass. Because the magnetic fields, we've had the capacity to measure that for quite a while. The same thing with strength of the electric field. Now, the radius, what the radius would physically represent would be where these particles are collected. So typically what you do is you set up a sensor over here, and you would have a collection point. So here's something that you might think about. It's like, okay, if I send a proton through, where is it going to be collected? If I send an electron through, what would that do to this magnetic field and the electric field and the magnetic field over here if I were sending electrons through? If I send an electron through over here, how would that differ in terms of not only the direction that it's going to curve, but also the radius that it's going to curve? So come back down here and be able to think this through in terms of, wow, what would happen if I had a more massive particle in that same magnetic field? Just something to think about. Okay, I've talked you through all of these, kind of hit the highlights. I'm going to send this out with this whole document. Best of luck to you, and tomorrow I will send out